So, welcome everybody. We're going to go over some basic pump selection here. Um, we're going to talk mostly about selection for regenerative turbine pumps, a couple different methods that we've put together for MTH that seem to work very well for us. I'm going to share some of those with you. We'll get going into it here. Before we get started, a few quick fun pumping facts. The largest pump in the world does 1 million gallons a minute, almost 60,000 liters per second. It requires a 5,364 horsepower motor. That's unbelievable. Smallest pump in the world is 1 nanometer in size. They use it for distributing medicine at a cellular level, and spins at 18,000 RPM. So, and then the highest pressure in the pump, or highest pressure pump in the world, rotodynamic, does almost 3,400 feet of head and almost 5,000 gallons a minute. Requires over 20,000 horsepower to drive. That's pretty significant. So when we talk, go ahead.
I would have liked to get that order, eh?
Yeah, no kidding. So talking about pump classifications, you've got basically your rotodynamic and your positive displacement. Rotodynamic means that there's rotating equipment involved, and positive displacement means that things are moving back and forth to make liquid move. So you've got your low head or your low pressure is an axial pump. Medium would be a vertical, horizontal, or centrifugal. Vertical and horizontal centrifugal pumps, and high head is a centrifugal pump or a regenerative turbine, and that's pretty much where we set in the scheme of the world of pumping. And then with the positive displacement, you've got your piston pumps, plunger pumps, gear pumps, screw pumps. Most of these are generally low flow with a higher head. Everything in the reciprocating will have pulsation, where gear pumps might have a little bit, but screw pumps don't really. What is a regenerative turbine pump? A regenerative turbine pump is a rotodynamic pump that combines the high discharge pressure of positive displacement pump with the flexibility of a centrifugal pump. So regenerative turbine characteristics, we have the high pressure, they're a compact design, simple construction. They usually only have about 3 major components: the cover, motor bracket, and impeller. They are pulsation free, so it's got a steady flow of water or whatever fluid you're pumping. They have the good NPSH characteristics, so that's net positive suction head, and then which gives them little to no cavitation. And we have a bunch of materials of construction available. A little bit about how they work. If you didn't see it in the session I held a couple hours ago, basically water goes into the center of a centrifugal pump, gets touched one time by the impeller vane, and then shoots out of the volute. With this kind of pumping method, you can hit relatively high flows, but you can't really hit that high a pressure. If you want to increase pressure, you would have to put multiple stacks of impellers in front of each other and have them run one at a time to build up that pressure. With a centrifugal pump, a single impeller can take in the water from the outside, from the peripheral of the impeller, and it works it over and over and over again, similar to the effects of multi-stage centrifugals, except it's doing it all in one impeller. And then it hits a water stop and exits out the pump at a much higher pressure than what it started with, but not necessarily as high of a flow. An example, here's a multi-stack centrifugal pump compared to a single stage regenerative turbine pump. You can see that regenerative turbine pumps in some cases can replace up to 25 stages on this particular example. Another comparison would be a rotary vane pump. If you're familiar with Procon or Fluidotech, they are rotary vane pumps, and we can compete with them pretty well. When it comes to NPSH, I talked a little bit about it earlier in the earlier session, but I'll get a little more into it here. Basically, when you have a situation where your water temperature starts getting higher, and you need to lower, less NPSH is available. You get to a point where a pump will start cavitating. With our flex-coupled regenerative turbine pumps, if you add a centrifugal impeller with a diffuser in front of the regenerative turbine pump, you'll end up having a much lower NPSH, in some cases all the way down to 1 foot, where it was previously several feet. Some quick conversions for those of you who are new to selecting pumps. When somebody tells you they have 100 PSI, we put all of our performance curves in feet of head or meters of head. So it would be 231 feet or 304 meters. Sometimes you have to convert bar as well. I don't come across that too often. But 1 gallon a minute is 3.78 liters. I don't know anybody who uses Kelvin, but we use Fahrenheit here, and 212 is boiling. I know in Canada you guys use Celsius, so that'd be 100 degrees. So things to watch out for. And then the most important parts of any kind of pump selection that you would need are you need the pressure, the flow, the temperature, and the fluid has to be clean. And if there's any other conditions to what you're pumping other than water, you really need to consult one of our application engineers, make sure all the materials are compatible, make sure there's not going to be some strange effects as temperature changes, so on and so forth. Your basic product line for MTH, we have our close coupled pumps, our P31, T31, T41, and T51. And then we have our multi-stage pumps, which are for the most part flex coupled. Some of our M series are close coupled, but also flex coupled. And then we do have a line of centrifugal pumps called our C series. It's a 4-inch, 5-inch, and 6-inch. And they have a variety of ranges that basically make it so that we can pump anywhere from a half a gallon a minute up to about 150 gallons a minute with our bigger pumps. But our pressures, we can go all the way up to 1,000 PSI with some of our pumps. So very first selection, or very first selection we're going to talk about here is boiler feed selection. This table is available on our website as well. But basically, if you have the boiler horsepower and the pressure that the system is running at, you can select a pump off of a table that should cover all of the bases for that particular boiler system. In this example, we have a 30 horsepower boiler, and it's running at 50 psi in the system. So a T31F on a 3rd horsepower motor would be able to maintain all the water needed in that boiler. Some of our base-mounted flux coupled pumps start getting into some of the larger numbers here. The main difference between the close coupled pumps and the flux coupled pumps, besides some of the pressures, are that the T series are all close coupled and they run at 3450 RPM, where all of our flex coupled pumps run at 1750 RPM, so half the speed for the driver. But they hit much higher pressures because they're multi-stages to these. In this example, we have a 25 horsepower boiler running at 15 psi in the system, so a 141D on a 3rd horsepower would work for that one. With a jockey pump, sometimes called a maintenance pump in a fire system, it's the secondary pump that just keeps the pressure in the system. It's not made to run if there ever is a fire. There's a bigger pump that does that. So we have a selection chart for that as well. If you know what the bigger pump's pump rating is, the main pump, in this example we have 1,000 gallons per minute, you would go over to what the system pressure is, and that system pressure is how much pressure is in the lines that are holding the sprinklers. When the system pressure is relieved, those sprinklers go off. When the sprinklers go off, it completely relieves all of the pressure and tells the system to turn on the big pump because there's a fire. And so you use a jockey pump to make sure that the system stays charged. Ways that a system would become not charged is if there's a leak somewhere, even if it's just a couple of drops an hour, can make a big difference over time and relieve that pressure. Or if you have a check valve that is allowing water to flow backwards in it and relieve some of that and letting some of that pressure out, you would have your jockey pump kick on, and usually they just turn on for a few minutes, and then once they put it back up to pressure, they turn off again. Another method of selection, when you're doing a pump replacement, in many cases we have cross-reference charts available for other pump companies' pumps versus our pumps. In this example, we have an MTH pump versus a Burke's pump. So we have a Burke's 7CT7M would cross over to a T41E 3/4 horse, 3450 RPM. And here I have an example of what a T31E's performance looks like compared to a Burke's pump. And you can see we can cover pretty much any point the Burke's pump hits, and even do a little better in some situations. And we also, because of the design of our pump, have better NPSH requirements than the Burke's pump does. Part of it's because with a Burke's pump, they're considered a regenerative turbine pump because they do the same flow of cycling water over and over again in a single impeller, but they do all of it on one side of the impeller. So they're a completely different design than what a regenerative turbine pump would be. I don't
Scott,
know how often. Yeah, go ahead.
are all these charts on the website?
Yes,
Like
every single
get
one
the
of these are on the
yeah.
website.
Okay, thanks, man.
Yeah. So over the last couple of years, we've learned that Aurora Pump is not making several of the models that they used to make. And as a result, we've seen quite an uptick in the amount of business that we've received for replacing Aurora pumps that have worn out or just time to replace the pumps because you can't really get parts for them either. And so in this example, we have the Aurora pump model K5, and it would cross over hydraulically to a 151K. The founder of our company, Dave Tremaine, actually worked at Aurora Pumps and broke off from Aurora Pumps to create MTH pumps. So he modeled a lot of our pumps off of Aurora Pumps. So that's why you'll see almost all the letters match up. G6 for a 161G and H6 for a 171H, so on and so forth. So we'll talk a little bit about selection of a single stage regenerative turbine pump here. The first thing to know when you're looking at sizing up a pump is that the most optimal operating range is between 50% of the pump's full curve all the way up to 80%. So from 0 to the 7 and 7.7 or so, 50% hits us at about 3.3 something, and then the 80%, that's the optimal range. So the first thing you do is you base all of your calculations off of the head first. So if somebody needs 300 feet ahead, you would go from the 300 feet ahead and draw a straight line over to where it intersects the head capacity, and then you would go down, and this pump would produce 5.4 gallons per minute. From there, there's a brake horsepower curve on all of our close coupled pumps that you would go straight down from where that intersects till it intersected the brake horsepower curve. And then you would go over and you would see that it hits just under 1 horsepower. So a 1 horsepower motor would be the motor you would want to use for this. When you want to look at what the efficiency rating is, you would do similar to the brake horsepower. You would go over from the 300 feet ahead. You would go straight up to the efficiency curve, and then you would go over to the efficiency table here, and you would see that this pump is going to be running at about 44% efficiency. Now, when you think about efficiencies for regenerative turbine pumps, you'll see almost all regenerative turbine pumps, hardly any of them hit over 50% efficiency. That's because they operate differently than a centrifugal pump, where a centrifugal pump is going to be competing at this pressure. Its flow is going to be much higher, and you'll be wasting a lot of energy in the amount of flow being wasted for that pump. So a lot of times when you choose a regenerative turbine over a multi-stack centrifugal, you end up with a much lower horsepower motor. So it's physically using less electricity to run the motor than a multi-stage centrifugal would be. Here's talking about some of the NPSH, the net positive suction head. When it's A, NPSH A, it's available. It's the amount of pressure that is in front of the pump. When it's R, it's required. That's how much the pump needs to operate. And atmospheric pressure at sea level is already almost 40 feet. So when you have a pump and the water level is the same level as the pump, you've already got 40 feet of NPSH available. It's when you start heating water up that the NPSH starts dropping. So when you get to about 180 degrees is when you only have 17 feet of NPSH. And that's when you'll start seeing the effects of some of the large pumps. When you get all the way up to 200 degrees, then you're at 7 feet of NPSH. Then you'd really start feeling or seeing the pump have trouble keeping up, and it'll start to cavitate. When you hit all the way up to boiling, at the point of boiling, you are at 0 here, meaning that the pump with the water level at the same level as the center line of the pump at boiling temperature is not going to be able to move because it's got no NPSH, and it will cavitate. That's why you would add the inducer, because the inducer will add several feet to that, putting it back in an operating range. With a centrifugal pump, because the fluid goes into the center of the impeller, when water starts to boil, it has and it forms the bubbles. Those bubbles take up the space of where water is supposed to flow, and water will completely stop flowing in a centrifugal pump when the NPSH is too great. With a regenerative turbine pump, as the NPSH becomes less available, because all of the work of the water is being done on the outside of the impeller, any of the bubbles that form from water boiling would just go out with the rest of the pump, and it would displace a little bit, but it would not completely stop operation of the pump. So here is if there was only 13 feet of NPSH, this is where you'd start seeing it degrade a little bit. With our 300 feet ahead, you can see that it would just go ever so slightly when it only has 13. But when it has 6 feet, then you go from the original 5.5 gallons a minute to about 5.25 gallons a minute. When you only have 4 feet of NPSH, then you really start to feel it. The pump will only be able to do about 4.5 gallons a minute. In many cases, like in a boiler feed situation, it can still keep up with that boiler at these 4 feet. But once you start getting past that, it might not be able to keep up. It's really dependent upon the system and how it's set up. Talking a little bit about our multi-stage centrifugal pumps. We use tables for these because there are 4 stages to each model, and we have 10 models of 150, 160, 170, and I think it's 10 models of the 140s and 180s. So we have all those times the 4 stages, and that leaves a lot of room for interpretation. So we've put it together in a table rather than try and put together a multi-stage curve, selection curve. In this one, if you need 75 feet ahead at 8 gallons a minute, 141E is the selection you would make. And then on the website, when you click on this, you would get to see the individual curve. Here's for the 150, 160, 170, which are much larger version. In this case, we want 150 feet ahead, but we want it at 40 gallons a minute, and we end up with a 151L with a 5 horsepower motor. When we look at the multi-stage curves, again, it's 50% to 80% is your most efficient point of the pump. So that's kind of where you want to stay in your selection area. If one of your selections is outside of this area, you really want to move up to the next larger pump that'll have a larger flow to select in that. So in this case, we have 300 feet at that same 5.5 gallons a minute that the T series was doing earlier. Here we do it with a 4-stage, and it would be the 5.5 gallons a minute. So each one of these lines is one of the stages. So it's a 1-stage, 2-stage, 3-stage, 4-stage. And then because there's already 4 lines on here, we separate out the horsepower to a different chart on the same page. So you would go over, determine your gallons per minute, and then you would go straight down to that same 4-stage pump, and then go back over to the left to see that it's a 1.75 brake horsepower, which would actually require a 2 horsepower motor to operate. And if you do add the 200 series inducer to lower that MPSH, it will require a 0.5 horsepower more to drive that impeller so that it works properly. So you would have to add a 0.5 horsepower to that. So in that case, you would actually have to go up to a 3 horsepower with this if you were to put that inducer on. Here with the NPSH, you can decide, so you've got your 300 feet ahead. The NPSH of the 140 series without the inducer is sitting at about 3.5 feet. If you are running water that is boiling and it's at the same level as the pump, that 3.5 feet is not going to be able to function correctly. So you'd put in a 200 series inducer, and that would drop that NPSH another 2 feet to give you back that NPSH. So we have the selection and then the horsepower. So we're at the 1.75, and then we'd add a horsepower or add a 0.5 horse to that. So it'd be 2.25. So you'd have to go up to the next size motor, which would be a 3 horse motor. One of the tables we have available on our website where we do show the curve family to be able to select is our M series. These are the pumps that can go up to 1,000 psi. They are based on a T51 impeller and water channel. So a single stage M series theoretically is the same pressure and flow as a T51. It's when you start adding stages that make it the higher pressure. In this case, we're going to select a M53E. So we're at 1,000 feet ahead. And the M53E here is going to do about 7.5 gallons a minute. To do the horsepower, it's very similar to the same way you would do horsepower for the multi-stage flex coupled is you would hit that 3-stage, and then you would see that you're sitting at about 5 horsepower motor. In this, we're showing the NPSH levels. So here with a M50 series, M53E, it would be a little under 5 feet. If you put in the L series inducer, it would put the NPSH down to 3 feet. So even though it's only 2 feet, it sometimes in a boiler feed situation, it can make a world of difference. So yeah, so here's the brake horsepower. Ended up being just under 5 feet. And then we also have relief valves. If you need to have your relief valve set at a certain PSI, we do have relief valves available. So you would set, if you needed 100 gallons a minute or 100 feet ahead. Sorry, I think that's in PSI. If you needed 100 PSI and you were doing 54 gallons a minute, you would need an 1.25-inch relief valve. So in this one, if you did 200 and you needed right around 100 gallons a minute, here we have 107, you'd need an 1.5-inch relief valve. So this would be PSI, this would be, and then all these numbers would be gallons per minute that it's rated for. Anything past this, it would redirect back to the supply tank. A little bit about our C-Series pumps. Here we have them 4-inch, 5-inch, and 6-inch. The way we designed our C-Series impellers is that they have an open face design, and they do not have any trims to them. So we designed the horsepower to fit the exact impeller. So they have designated motors for each horsepower. So this curve along the whole curve would do the same horsepower. Example of that, here's a C41CD, and the best efficiency point for it is sitting right here at about 35 gallons a minute, and that's at 42 feet ahead. You can see with our centrifugal pumps, because of the open face design, they still keep relatively low NPSH, and the brake horsepower starts at a 1/3 horse and goes all the way up. Even though it goes well past a 1/2 horse, there's a service factor to all our motors that we use for these C-Series that keep it back within range. So this pump can literally run anywhere in this point from all the way from being closed off with no flow all the way until it has run out at the 52 gallons a minute, and it won't hurt the pump to leave it any pressure in between that. And that is just about it. This one was quite a bit shorter than the last one. Does anybody have any questions? I'm going to go ahead and unmute everybody. And if you have any questions, please feel free to go ahead and.
Scott, just a quick oversight on the C-Series.
Yeah.
There's no published minimum flow on those, right? Like you can't run
Right.
them dead, right?
Oh, if you did deadhead them because of the open face design, you would not hurt them, and they will maintain the horsepower without hurting it. It just won't flow. So
okay, so it
if you get
just recirculates across the face of the impeller.
Yep.
Okay.
And since they're centrifugal pumps, they don't generate too much heat. So it's not recommended because you're just wasting energy. But if you were to leave it on, it wouldn't do any damage to the pump.
That's interesting. Okay. And the other thing here is that we had some DOE issues on this one too, right?
Yeah, I think, well, we had, when the Department of Energy came out with their new rules, we had to eliminate, I think, 3 models, and we eliminated them because they had almost no sales, and all of them had another pump that could cover what they were doing. And so all the rest of them with the Department of Energy, we publish what the um, pump
Yeah.
efficiency rating is. So it's published right on the curve when you go to our website.
Okay, but didn't you guys have an issue where you can't sell them into Canada?
I think there's a couple of our T series that they do that. Let me show you. So here's our website, and some of our T series, we'll go to the close couple first. So I think it's some of our higher T series where we have this DOE compliance is a 0.13. I think there's a limitation to what you guys can sell into. And so like this one particular model, this R, I think it's the P and maybe the M. I think these are the only 3 models you guys can't sell into Canada. And that's only if the suction is on the front. The way these are designed in stainless steel, they actually have a flat top on them, so we could cut a top suction, top discharge in these if you really needed this pressure.
Right. Okay.
And then all of the flex couple are completely clear. And then for the close coupled, I think there was some of the larger pumps that where we had to publish a pump efficiency here. But I think this 0.87, I think we can sell these to you. The one pump that we cannot sell is actually on our 12-volt motor. And that's not to say that we couldn't put a different C-series pump end on a 12-volt motor for you if we needed to. It's just that one particular pump size is not approved for Canadian sale.
Okay.
And it doesn't mean that we couldn't ever sell them. There's some certifications that we would have to go through the NRCan, the Natural Resources of Canada, and have to get certified in. The issue we ran into is that they are very, very, very expensive.
Yeah, it's ridiculous, but anyway, it is what it is.
So
Okay.
anyway, do you have any
And
other questions? If not, I think we are good now. If anybody has any questions or if anybody wants a copy of this presentation, please email me. I believe everybody. Well, yeah, if you got the email for the invite for this webinar, you've also got the my email address. So please feel free to email me if you'd like a copy of this presentation to look over or go over again with some of your team. If that's all, thank you very much for the time, and we are having another set of these sessions tomorrow at 2 o'clock and at 4 o'clock. If you're interested, please register on the email for them. Until then, let me know if you have any questions, and again, thank you for participating in this, and have a good afternoon.
Thanks, Scott.
Yep.
Thank
thanks.
you.
Sure.